Exercise number 1.1, question number 1. What they are asking in all these questions, determine whether each of the following relations are reflexive, symmetric, transitive. That means we'll take one relation first and then we'll check that relation is reflexive relation or symmetric relation or transitive relation. These things we'll check for each bit in this first question. They given R is a relation on set A. That means they given set A here. First point, you write that one. Yes, what is set A? Set A is 1, 2, 3, 4, like that up to 14. This is the given set. Second point is this relation is from where to where. You observe R is a relation in the set A. That means R is a relation on A. It means that R is a relation from A to A. This point also important. You write that point. Given that R is a relation on A, R is a relation on A, it means that R is a relation from A to A. Okay. Third point, given relation. You observe this is the given relation. You write that one. See, this is the given relation. In all these bits in the first question, these three steps you need to observe carefully. Okay. Now I need to check this relation is reflexive relation or symmetric relation or transitive relation. All those three things I need to check for this relation. Here, whatever the things we learned till now in this chapter, in all those examples, the relation is in roster method like 1 comma 1, 1 comma 2, 2 comma 3, something like that. If the relation is like this, then we can easily check the relation is reflexive or symmetric or transitive, right? But this relation they given in set builder form. Elements are represented with its property. So the point is you need to write this relation into roster method. Then we can easily check the relation is reflexive or symmetric or transitive. Okay. To write this relation in roster method, you observe these order pairs. Here R is a relation on A. Na? As R is a relation on A, R is a subset of A cross A. So here the point is X is in set A. X must belongs to set A. Y also must belongs to set A. X we can write 1, 2, 3, 4 like that up to 14. Y also we can write 1, 2, 3, 4 like that up to 14. You cannot write y as 3 by 2 because 3 by 2 is not in this set A. As R is a relation on A, these two elements must belongs to set A. Okay. And one more thing, these two elements must belongs to this set A. And one more thing is this order pair must satisfy this condition. Whatever xy values we'll choose from set A, that must satisfy this 3x minus y equal to 0. So what I'll do to do this further, this 3x minus y I write separately. See, they given in the question 3x minus y equal to 0. From that, what is y? Y equal to 3x. Now, keep this point in your mind, y equal to 3x. I'll start writing this relation into roster method. You know that x is from set A. So, I'll take first element of set A, that is 1. Okay. When x is 1, what is y? As x is 1, that x value you substitute in this y equal to 3x, right? Put x equal to 1 in this, what you will get? Y is 3 into 1. That means y is 3. That means when x is 1, listen carefully, when x is 1, y is 3. So the first order pair what we will get is 1 comma 3. You observe one thing, this is there in set A, 3 is also there in set A, and when I substitute 1 comma 3 in this equation, it must and should satisfy. See, x value 1, y value 3, substitute in this 3 into 1 minus, in place of y you write 3. So left hand side is 3 minus 3, 0, 0 equal to 0, satisfying. So this order pair 1 comma 3 belongs to this relation. Actually, this relation is in set builder form. I am writing this relation into roster method. Roster method is what? Set of all elements are listed like this. 1 comma 3 is one element. Now, I need to take second element in this relation. Here you know that this x is from set A. As already 1 is over, now you take 2. in place of x, now x is 2. In this, in place of x, you write 2. Then what you will get? Y equal to 3 into 2. 3 into 2 is 6. So second order pair is 2 comma 6. If you observe this 2 and 6 both are there in this set, and when I substitute this 2 comma 6 in this, it must and should satisfy. It satisfies because this we are getting from this only. So you put x equal to 2 and y equal to 6 in this. 3 into 2 minus 6 equal to 0. See, 6 minus 6, 0 equal to 0, satisfying. So order pair 2 comma 6 belongs to this relation. Similarly, you take x is third element, x is 3. Put x is 3. When you put x is 3 in this, what you will get? Y equal to 3 into 3, y equal to 9. So this order pair is 3 comma 9. Similarly, you take x is 4. Put x is 4 in this. 3 into 4 is 12. Y is 12. So this is 4 comma 12. After 4, you take x is 5. 5 is there here. You take x is 5. When I substitute x is 5 in this, what I will get? Y is 3 into 5, 15. So this order pair is 5 comma 15. But the problem is, to be this order pair is will be in this relation when these two numbers must be in set A. Here 15 is there, 15. 15 is not in set A. So the order pair 5 comma 15 does not belongs this relation. It doesn't belongs this relation because the 15 is not in this set A. This says that as it is a relation on A, x must be in set A, y also must be in set A. Similarly, if I take x is 6, y will become 3 into 6, 18. As 18 is not in set A, this doesn't belong to this. 8, you take 7, x is 7. When you put x is 7 here, y is 21. 21 is also not in this relation. So these things, whatever further order pairs we'll get, when I take x equal to 8, x equal to 9, whatever order pairs we'll get, those order pairs does not belong to this relation. I hope you understand. So what happened? I written the given relation in roster method. You observe in this all order pairs are listed and separated by commas. In this set total 4 elements are there. Okay. Now it is easy for us to check the relation is reflexive or symmetric or transitive. Now I'll check this relation is reflexive or not. What is reflexive relation? For every x in set A implies order pair x comma s, x must belongs to relation. This is what we learn in second class reflexive relation definition. For every x in set A, order pair x comma x must belongs to relation. Here, what is set A? Set A is like this. You need to check for every element in set A that respective order pair x comma 1, x comma x belongs to the relation or not. Now, I'll take 1. For 1, 1 comma 1 is there in this relation? No. As condition of reflexivity fails here, directly I can write here this relation is not reflexive, right? I'll write here. What is the reason? For 1 is there in set A implies the order pair 1 comma 1 does not belongs to the relation. Because of this reason, I can say that R is not reflexive. In this particular example, it is not compulsory you will write like this. You see, in this set 2 is there. Order pair 2 comma 2 is also not there. So you can write like this also. 2 is there in set A implies 2 comma 2 does not belongs to relation. Here 1 comma 1 does not belongs to relation. For 2 belongs to set A, 2 comma 2 does not belongs to relation. Therefore, this relation is not reflexive. Like that also you can write. See, when the relation is not reflexive, identifying and writing the answer is very easy. When the relation is reflexive, for example, here 1 is there in set A. If 1 comma 1 also present in this, based on that, we cannot declare it is reflexive because you need to check for every x in set A, order pair x comma x belongs to relation or not. For 1, 1 comma 1 is there or not. If 1 comma 1 is there, for 2, 2 comma 2 is there or not, we'll check. For 3, 3 comma 3 is there, like that we'll check. We need to check for every x in set A. We'll check for every x in set A. Okay. Now, I need to check this relation is symmetric relation or not. What is symmetric condition? Symmetric condition is for every order pair x comma y in the relation, y comma x also must belongs this relation. This is what we discussed in the theory part, right? So for every, this is important, for every order pair x comma y in the relation, y comma x belongs to the relation or not, we will check. If this holds good for every order pair x comma y, then we say that this is symmetric. Okay, now this is the relation. You take one order pair in this. For example, here 1 comma 3. Yes, let 1 comma 3 from the relation. 1 comma 3 belongs to R. For respect to 1 comma 3, 3 comma 1 is there in the relation or not? You check. 3 comma 1 is there? No, it is not there. So we can say that this relation is not symmetric. One more point here. For 1 comma 3, you suppose 3 comma 1 is there in this relation. From that, can I say it is symmetric? No. You need to check for every order pair. In that case, we say that this element passed the symmetric test. Now we'll come to 2 comma 6. For 2 comma 6, 6 comma 2 is there in this relation? No. So we say it is not symmetric. But for first order pair x comma y comma x is not in this relation. For 1 comma 3, 3 comma 1 is not in this relation. When one element satisfies to fail symmetric condition, then we say that it is not symmetric. Here 1 comma 3 is there in this relation. That implies 3 comma 1 does not belongs to the relation. So we say that this relation is not symmetric. Okay, I checked, this relation is not reflexive. I checked a symmetric condition. I came to know that this relation is not symmetric also. Now I need to check transitive condition. What is transitive condition? For every order pair x comma y belongs to R and y comma z belongs to R, then we look for x comma z is there in the relation or not. For every such order pair, if x comma z exists, then we say that relation is transitive. Now, what I'll do here, I'll come with this first order pair. You observe this ends with 3. Now, you look at any other order pair in this relation which starts with 3. Yes, here it is. This starts with 3, this ends with 3. That means we are able to find x comma y, y comma z. X comma y comma z, we are able to find. So what I'll write here, let 1 comma 3 is there in this relation and we are able to find 3 comma 9 also. When such order pair exists, then only we look for x comma z. 1 comma 9 is there in this relation. 1 comma 9 is there in this relation. You look that 1 comma 9 is there in this relation. No. That means for x comma y and y comma z, x comma z does not belong to this relation. So we can say that this relation is not transitive. So what I can write from this, 1 comma 3, 3 comma 9. 1 comma 9 does not belong to this relation. Therefore, this relation is not transitive. So in this question, they are asking us to check reflexive symmetric transitivity of this relation. This relation is not reflexive. This relation is not symmetric. This relation is not transitive. We need to check that whether this relation is reflexive or symmetric or transitive. Okay. You observe in this question, they are saying that relation R in the set of all natural numbers. So R is a relation on set of all natural numbers. So as I said in last problem, we need to observe 3 points. In that, first point is relation is on which set. In this question, relation is on set of natural numbers. So you know what are natural numbers, 1, 2, 3, 4, like that. All counting numbers are natural numbers. Okay. And they are saying R is a relation on set n. So I'll write that also. R is a relation on n means R is a relation from natural numbers to natural numbers. Okay. And the relation they given like this, we'll write this also. You observe this relation. This is similar to last problem. Here, this relation is given in set builder form. This relation contains order pairs, right? As this relation, as it is a relation on set of all natural numbers, x is a natural number, y is also a natural number. Both these elements must belongs to this set. Okay. And here you observe this order pair must satisfy these two conditions. You observe x is a natural number which is less than 4. X is a natural number and less than 4. That means x you can take 1, 2, 3. You cannot take 4 because they are saying x is strictly less than 4. So I'll write this relation into roster method so that I can easily check reflexive symmetric transitive condition. So here x is less than 4, they are saying I'll take x equal to 1. First point, 1 is a natural number, okay, and 1 is less than 4. I'll put this x value in this. Put x value 1 in this, what you will get? Y is 1 plus 5, 1 plus 5 is 6. So first order pair is 1 comma 6. What point you need to observe? The order pair 1 comma 6 belongs this relation. Why? Why? Because 1 is a natural number, 6 is a natural number, and this x is less than 4, and this order pair 1 comma 6 satisfies this condition. If you want, you can check. In place of x you write 1, in place of y you write 6. Y equal to 6 equal to 1 plus 5. Definitely it satisfies, right? Okay. Now as x is a natural number and less than 4, I'll take x is 2. You take x is 2, put x is 2 in this. What you will get? 2 plus 5 is 7. So this order pair is 2 comma 7. Now as x is a natural number and x is less than 3, I can take x as 3. You take x as 3. Put x is 3 in this. 3 plus 5 is 8. So this order pair is 3 comma 8. You cannot take x equal to 4 because they are saying that x is a natural number and x is less than 4. You cannot take x equal to 4 because x is less than 4. So this relation is completed. They given this relation in set builder method. I written this relation in roster method. Roster method means all the elements are listed. It is more clear now what elements are there in this relation. Okay. Now you need to check this relation is reflexive or symmetric or transitive. It is very easy for this problem. How to check a reflexive condition? What is the definition of reflexive relation? For every x belongs to A implies order pair x comma x belongs to R. In this question, this A is natural numbers. That means for every x belongs to n, you need to check that order pair x comma x is there in the relation or not. Okay. First, I'll take 1x from this natural numbers. I'll take 1. Order pair 1 comma 1 is there in this relation? No. Order pair 1 comma 1 is not in this relation. So what I can say, for 1 belongs to natural numbers implies order pair 1 comma 1 does not belongs to the relation. From this, you can say that the relation R is not reflexive. Now, I'll check symmetric condition. What is symmetric definition? For every order pair x comma y, this is important. For every order pair x comma y comma x also there in the relation or not, you need to check. Okay. Here, this is the relation. I am checking this relation is symmetric or not. First, you take one order pair, 1 comma 6. Yes, 1 comma 6 is there in this. Let 1 comma 6 in the relation. For 1 comma 6, 6 comma 1 is present in this relation. No, 6 comma 1 does not belongs this relation. So what I'll say, 6 comma 1 does not belongs this relation. That means this element fails to satisfy symmetric condition. So we say that this relation is not symmetric. So given relation is not reflexive and given relation is not symmetric. Now I'll check transitive condition. In this problem, transitivity is the tricky one. Observe the definition first. For every x comma y belongs to R and y comma z belongs to R, we look that x comma z is there in the relation or not. This is transitive condition, correct? Okay. Now if there doesn't exist such ordered pair, x comma y comma z doesn't exist in the relation, in that case, no need to check for x comma z. We say that that relation is transitive. You try to understand. If there exists an order pair x comma y comma z in the relation, then only we look for x comma z. If there doesn't exist x comma y comma z in the relation, then no need to check this condition and we say that that relation is transitive. Let's see this relation. You observe here, you observe this order pair ends with 6. Now you look that any other order pair starts with 6 in this relation. There is no other order pair starts with 6 in this relation. So that means for this x comma y, there doesn't exist y comma z to check x comma z. In that case, we say that this element passed the transitive test. Okay. Now come to this order pair. This ends with 7. you look that any other order pair starts with 7 in this relation. No other order pair starts with 7 in this relation. That means for the order pair 2 comma 7, there doesn't exist any other order pair which starts with 7. That means for x comma y, there doesn't exist y comma z. So no need to check for x comma z. So in this case also, we say that this relation is, this element satisfies transitive condition. Now come to this third order pair. This ends with 8. Any other order pair starts with 8? No. So we say that this element passes the transitive test. So overall, we identified that there doesn't exist x comma y belongs to R and y comma z belongs to R in the relation. So there is no need to look for x comma z. I hope you are understanding. You observe this clearly. For every order pair in the given relation, there doesn't exist y comma z. That means x comma y comma z does not exist in this relation. In this case, we say that the given relation is transitive. I discussed so many examples in the beginning of explanation of definition of transitive with the help of examples, right? Here, if I explain again, it is lengthy. You please check that video once. Definition of transitive relation and examples. So when we are unable to find x comma y comma z in the relation, in that case, we say that the relation R is transitive. So this relation is not reflexive, not symmetric, but it is transitive.